I'm going to make 3 videos for the organic chemistry topic. One is going to be about crude oil and sort of carbon as a fuel and feedstock, all this kind of stuff. A little bit about where crude oil comes from, what it's made of, so mixtures of hydrocarbons, how then those hydrocarbons are processed by fractional distillation first of all, where you need to do a fair bit of detail, and a bit more on cracking, and we'll talk about what you get when you put long chain hydrocarbons through this cracking process as well. We'll then in the second video talk about organic reactions, which is a bit more involved, a bit more advanced, and is only covered by the triple course, and then we'll look at polymerization, addition and condensation polymerization, one of the trickier topics of the whole course, I would argue. Right, okay, so we'll start off by talking about crude oil. And the first point is just say what it actually is. It's a mixture, lots of different hydrocarbons. So it's a mixture of hydrocarbons. And those hydrocarbons, well, let's be clear what we mean by hydrocarbons. We're expected to be able to define hydrocarbons. Hydrocarbons are molecules, so simple covalent substances made up of carbon and hydrogen atoms only. So they're compounds made of hydrogen and carbon atoms, and to get 2 marks on that, you've got to say only. So things like alcohols which have an oxygen in aren't hydrocarbons, because they're not only hydrogen and carbon, right? So you need to know a little bit about crude oil. You'd have covered this in minor detail, but it is one of those things that can be asked. So it's worth getting that down on a revision card and practicing it. You have to have a pretty clear idea that crude oil, first of all, is a fossil fuel, and you need to know what a fossil fuel is. And the idea is that it's a fuel made from something that died a very, very long time ago. And there's lots of links in organic chemistry to other topics, such as bonding. There's a few links in there which I'll try to draw attention to. There's also links to the resources topic, for example. So fossil fuels are finite resources. They will run out eventually, inevitably, because there's only so much of them, and they're not being replaced as quickly as well. They take millions of years to replace. So you need to know how they form in very, very simple terms. Just the idea that it's the remains of creatures that lived a very, very long time ago, millions of years ago, specifically. And I've seen this in a mark scheme which I'll show you in a sec, but it's the idea that mostly it's plankton that died millions of years ago, and it's millions of years. It's the idea that it's a really, really long time ago, and these died and got buried in sediment, and so let's make a note of that. So buried in sediment, covered with rock, in other words, and then over millions of years, as I've said a few times now, huge pressure, high pressure and temperature meant that those the carbon molecules that were existing within those living creatures from a long time ago squished together a huge pressure and temperature, and eventually turned into these mixtures of hydrocarbons, which is what crude oil is. Now, crude oil can therefore be drilled up. Now it can be pulled out of the rock. You need to know how that happens, but it's in itself is fairly useless. There's not much you can do with crude oil directly. It has to be processed. And that's what we're going to talk about next. Before I do, though, I'm just going to show you an example of a couple of questions on something like this. There's a question here. There's natural gas as a fossil fuel. Describe how deposits of natural gas were formed. And you get a mark in this is from a 2022 paper, and you can sort of make the same arguments about natural gas as you would crude oil. And you'd have to say that plankton died, or tiny marine organisms died. That's 1 mark. So you have to say the plankton, the idea of plankton being important there. And very few people got that mark, actually. So plankton died and then fell to the bottom of the ocean. And then the next mark was to say they were covered in sediments. And then the idea that I've mentioned a few times, high temperature and pressure for millions of years. And that's how you get 3 marks on a pretty straightforward question like that. You could add some detail to it, the idea that they were, this was all happening under anaerobic conditions, so there's no oxygen present, but that's what you need for the 3 marks. And actually that was a question that was done relatively badly a couple of years ago nationally, okay? So worth mentioning. Right, so how is crude oil, that thick, black, sticky, gloopy mixture of hydrocarbons, processed? Well, the first thing is it's got to be converted into different fractions. And I think the best thing I can do is to show you a picture which you've all got in your revision guides anyway, but I'm going to draw your attention to a couple of points. Okay, so rather than me draw it out, I'm going to show you this. It's a very, very simplified idea of what a fractionating column looks like, but it really clearly sets out the things you're expected to know. So I'd be writing revision cards on each of these things, but I'm going to point out a couple of things to you. The first is that the crude oil is pumped in from the bottom, and that's often missed. People think it, well, I don't know what they think, but look here, this is really a bit vague, I think, in the revision guide, but it's really important you understand that the crude oil, which is a thick, gloopy liquid, if you shove that into the bottom of this thing, it'll just be a bit of a mess. But what they do is they heat it up first, and the whole idea is that these long and short and various length hydrocarbons, all of which are represented on the left-hand side here, this is what these hydrocarbons are supposed to look like, according to the revision guide, that they're heated before they go in, and the vast majority of them are turned into gas before they're put into the fractionating column. And so that's all except the very heaviest, very longest chain hydrocarbon, which is bitumen, sometimes called residue. Okay. So the rest of them, except the very longest chain one, will be a gas, and therefore they'll rise up this column, which has a temperature gradient. Important idea, that it's very hot at the bottom and cold at the top. Now, when they cool down, I think you know that when gases cool down, eventually they'll turn into liquid. So when they get cool enough to turn into, or when they get cool enough to reach their own boiling point, which is the condensation point, which is the same as the boiling point, they will turn into a liquid, and they will be pumped off and used for the various things. So hot at the bottom, turned into a gas first, and then as they go up, they condense. But the medium chain ones condense in the middle, the very short chain ones condense at the top. Now this links to the bonding topic, because you have to have this idea that long chain hydrocarbons have relatively high boiling points. They are simple covalent, so they are relatively low compared to ionic or metallic substances, for example. But compared to short chain hydrocarbons, these have higher boiling points. And that's because they have higher or stronger intermolecular forces between molecules than the medium and short length ones do. Okay, that's just a link to the bonding topic, as much as I'm going to mention for now. You need to know the order of the fractions and what they're for. So bitumen is used to make roads. Fuel oil can be used for a number of things, including lubrication, heating oil, fuel oil, powering ships, I think, as well. Diesel oil, obviously lorries, some cars, trains. Kerosene, mainly aeroplanes. You can get kerosene lamps as well. And of course, petrol, you're, I'm sure, aware of, used for cars. And you get this stuff, liquid petroleum gas, which is propane and butane. You get that in cooking gases. If you've ever been camping, you've probably taken an LPG burner with you. Okay. Now you need to know some differences between these fractions as well. So the long chain at the bottom, short chain at the top, high boiling point at the bottom, short boiling point at the top. Very thick and sticky and viscous at the bottom, again because of their strong intermolecular forces. Very volatile, we say. So rather than viscous, up here it's volatile, which means they turn into a gas easily. The fact they turn into a gas easily means that they can burn more easily. So easy to ignite, hard to ignite. And all of that is set out on here there. So I'm not going to write all this out. You can pause it and make a note of this if you need to. But what I would do is test yourself to make sure that you know short chain, long chain, short, low boiling point, high boiling point, and so on, like I just went through. Okay. Okay. You need to know what those uses are, which I've just been through on that page. And that's probably as much as I'll say about fraction distillation at this point. Make sure you can label one of those diagrams pretty well. Here's an example of a question, again from 2022, where the fractionating or fraction distillation of crude oil is discussed. So here's some examples: lubricating oil, naphtha and petroleum gases. Notice they've thrown ones at you that you haven't seen before. That's not unusual. So you've not heard of naphtha, possibly. That's not in the revision guide or the specification specifically. Petroleum gases is just petrol, lubricating oil, another word for some of the heavy fuel oils. Okay, and it tells you their boiling point ranges, and it's worth noting here that the boiling points are ranges because there's more than one hydrocarbon length within a fraction, and you have to explain for 4 marks how the fraction of distillation is used. So the first mark is, as I said a moment ago, it's to heat the crude oil. And why? Why do you have to do that? And then the whole point is to vaporize. So that's what the mark was for, the first mark, to vaporize the crude oil. Or it says in the mark scheme the hydrocarbons, but that's fine. And then the second point, which again we talked about, is this idea there's a temperature gradient. Ideally, I'd like you to know that it's hot at the bottom, cold at the top. Or you could simply say it is cooler as you go up the fractionating column. And then you say that the different fractions condense at different layers. Or you could say so they condense, the fractions condense at different levels or layers. And that's due to the differences in boiling points. Okay, a bit further on that question. Question 4 says you need to know the uses, or be able to work out the uses of the fractions. Fractions can be used to produce feedstocks for the petrochemical industry. In other words, they can then be further processed to make petrol that we can use in cars. So pick out 2 useful materials produced from crude oil. That's massively easy. That one of them is detergents, but you can work out, that alloys are mixtures of metals, so you know that ceramics are inorganic molecules. Fertilizers you might not have studied yet, but fertilizers primarily made from ammonium nitrate and ammonium sulfate, and the other one is solvent, so those 2 marks there. And there's a question about combustion of hydrocarbons, so it's worth mentioning this now as well then. So when you burn hydrocarbons, they always produce, if it's complete combustion, carbon dioxide and water, and that happens if it's complete combustion when you've got plenty of oxygen, lots and lots of oxygen there, and all you have to do is balance this equation. This isn't particularly easy to balance, but it's only possible really, or to do it sensibly, as long as you get the right product. So the whole idea is here, you understand that all of the carbon atoms are fully oxidized to carbon dioxide, and all of the hydrogen atoms within the hydrocarbon are also fully oxidized to water. So let's balance this. Let's balance the carbons to start with by saying we've got to have 9 carbon dioxides for every one of these. And there are 20 carbons, so we must have 10 waters. Can't have the oxygen, so we can work backwards. So 18 add 10, so that's 28. So hopefully I've got it right that it's 14 oxygens there. The sulfur question I'm going to ignore right now. That's part of the atmosphere topic, which we'll consider another time. A couple of other questions about fractions over here. You're told about two more fractions. Kerosene, which is one of the ones we are aware of, it's used to make aeroplanes, and heavy fuel oil, which is we know about, used as lubricating oil and possibly powering heavy ships, that kind of stuff. And it tells you the number of carbons this time. So these are ones at the bottom of the column, or near the bottom of the column, and these are just a little bit higher up the column, the fractionating column. And it says that a student predicted that heavy fuel oil is more viscous. You have to know, don't you, that longer chains are more viscous, and that's right. The student's prediction was correct. You've got to justify it though. And then really you've got to say is as the molecular size, or the chain length if you like, molecular size increases, you get an increase in viscosity. So that's the fact that we've learnt, and all you've then got to do is link that to the information you've been given in the question. And heavy fuel oil, which I'm just going to call HFO, has longer chains, or more carbons. than kerosene? Such a straightforward question, but it was not answered particularly well, I would argue. There's some more questions I'll come back to in a sec on cracking. So what about cracking then? So cracking, the whole point of cracking is to make as many or as much use out of that crude oil as we possibly can. So we've already talked about the fact that there are some short chain hydrocarbons and long chain hydrocarbons. And I'm going to represent the short chain hydrocarbons with little short zigzaggy lines, medium length ones, medium length zigzaggy lines, and then the long chain ones can be longer zigzaggy lines. And you have to understand that these short chain, easy to ignite hydrocarbons have lots of uses, particularly around fuels. Okay, so there's a very, very high demand for them. You can sell them and make loads of money without any issue at all. And it's the same for the medium length ones. There's lots of uses for them. High demand, lots of money can be used. So cooking gases, maybe petrol, that kind of thing. These longer chain ones, where we've maybe got 30 or 40 carbons, something like that, they ain't so useful. They're not so many uses of them. There are uses of them, lubricating oil, the heating oil, that kind of stuff we talked about, but there are fewer uses of them. And so the key word we need to put here is that the demand is relatively low. Doesn't mean they're useless. There's fewer uses. Important distinction. So we talk about demand, we talk about the fewer uses compared to the shorter chain ones. And so you can turn these long chain hydrocarbons, which I'm going to represent with a kind of chemical equation now, silly sort of made up one. So long chain hydrocarbon into a shorter chain hydrocarbon, something like that. And you also get another type of hydrocarbon, okay, which is however many carbons there were over here, you get carbons over here. And one thing we've not talked about yet is that hydrocarbons are all, or we can think of them all as being alkanes. In other words, there's no double bonds. When you do cracking, you get an alkane, and you can get alkenes as well, and that means they've got a double bond in. I'm going to talk about those in a bit, but I want to get the idea across initially that long chain hydrocarbon, so long chain alkane into shorter chain alkane and shorter chain alkene, and that some of the carbons over here is the same as the sum of the carbons over here and here. Also, however many hydrogens there are, I'll do a specific example of this, and again I'll talk in a bit more detail about the formula of alkanes and structure and so on in a sec. C20H42, and we'll see why that makes sense in a bit, might be converted to say C15H32. So the other molecule must have 5 carbons because 15 of the 20 have been used there, and it must be H10 because 42 of the hydrogens have turned into 32 hydrogens in this molecule, so there must be 10. So 15 and 5 is 20, 32 and 10 is 42. Okay, so that's the process that's going on in cracking. You need to know a little bit about how cracking is done, and you need to know why it's done, and you need to know the uses of the product. So low demand because fewer uses, much higher demand because there's more uses, possibly because it's got a slightly lower boiling point, more volatile, easier to ignite, uses petrol. And then the other thing that you make is an alkene, which we'll talk about in a bit. These are particularly useful because you can make loads of chemicals from them. They're quite reactive and you can use them to make polymers and all sorts of stuff like that. Okay, let's talk then about how cracking is done. And I would really recognise that this is quite difficult to remember all of this. You probably have to practice this, learn this, get your head around it. So cracking, it's worth being able to kind of have an idea of what the diagram of cracking looks like. It's unlikely you'd have to draw it yourselves. It's also unlikely you'd have done it in the lab these days because it's now banned for students to do in the lab. It might be that it's been demonstrated to you, and I've drawn that really badly, but never mind. So what I'm drawing is a test tube on the left, which is kind of more or less horizontal, and it's got a bung, which I've drawn badly, at the end with a delivery tube going through it. This is a delivery tube. And the delivery tube goes into another test tube, which is inverted and in a trough of water. And what happens is that the crude oil is usually sort of soaked into a piece of mineral wool, so down here, so the crude oil or the longer chain hydrocarbon. So often they would use something like paraffin, which I probably spelled incorrectly, but never mind. And you might have some sort of catalyst here, and you need to heat that catalyst and probably heat the crude oil a little bit to turn it into a vapor, but you've certainly got to heat the catalyst, which is sitting there. And then what will happen is the vapors, so you're probably heating this a little bit as well, the vapors travel across the catalyst, and when they do so they undergo that chemical reaction, splitting them, breaking them apart, so it's thermally decomposing them, so this is thermal decomposition. The molecules travel then as gases through the delivery tube into the inverted test tube, which by the way was full of water, and then the gases bubble up and end up in that test tube. And you can trap the gases in that test tube by putting a bung in while it's still underwater, and you can test to see what you've made. Okay, and I'll talk about that when I get to talking about alkenes in detail. But you need to know a couple of ways of doing cracking that are done industrially. So the first idea is getting this idea that it's thermal decomposition, thermal heating, decomposition, breaking down. So whatever process you use to break down the long chain hydrocarbon, it's going to be heat involved. It could be that you do it catalytically. So it could be catalytic cracking, and you pass the vapor over a hot catalyst. That might be something like aluminium oxide, but you wouldn't be necessarily expected to know that. Sometimes it uses something called zeolites, which are aluminium oxide substances. And that the idea of using a catalyst keeps the temperature relatively low because the reaction is faster at a lower temperature, and means you don't have to heat it quite as much. But you can do cracking under different conditions, such as steam cracking, and these are the two, by the way, the exam board want you to know: catalytic cracking and steam cracking. And the idea is you mix the vapors with steam, and then heat to a very high temperature. So again, it's heating with steam essentially. And you've got to think, why might they do cracking in different ways? This sounds like quite an expensive way of doing it. You've got to heat up not just the crude oil to a very high temperature, but also water as well. It's got a high specific heat capacity. Why would you want to do that rather than just do it over a catalyst? Well, it might be that you get a different ratio of products. So instead of getting C15 H whatever it was 32, it might be that you get a slightly different number of carbons in the alkane and the alkene that you produce. But you've got to know two ways of doing it. Both, the thing that's similar between them is they both involve heating. This is an absolutely standard question on this. 3 marks for this, what I've just covered, you can easily easily get 3 marks for. So what's the process which produces smaller hydrocarbons from heavy fuel oil? The name of the process is cracking. That's 1 mark. You just have to know it. And the conditions, you've got a choice of 2 conditions. Both involve high temperature, so there's going to be a mark for high temperature. Don't just say heat, say high temperature. And then you've got a choice of either doing it with steam, or you could say you had a catalyst. Whichever you decide to do, you've got to do either one of those. So 1 for that, or that for the 3rd mark. And then you're told you've got hydrocarbons containing 7 and 8 can be made when heavy fuel oil is processed. So this one is asking you about something I haven't told you yet, so I'll come back to that in a second. Right, so I've told you about cracking being used to make alkanes and alkenes, it's worth now covering what alkanes and alkenes are. First of all, alkanes are chains of carbon atoms where all of the carbons are making 4 single bonds, and either they're making a bond with a carbon or possibly 2 carbons, or they're making bonds with hydrogens. But the key idea is that every carbon is making 4 bonds, and you need to know and be able to draw and name 4 alkanes. That's it, and draw them without mistake. And sorry, this is taking me a long time. Hopefully you can fast forward it. There we go. There's the 4 that you need to be able to draw. Make sure you can draw them. Good thing for a flashcard, I would say. And name them. So this is methane, monkeys, ethane, ane because it's an alkane, propane, peanut, and butane, butter. Monkeys eat peanut butter. So know those. There are others, of course. You get longer chain ones: pentane, hexane, heptane, and so on and so on. You do need to know those. You do need to know a tiny bit about alkenes for trilogy and much more for triple. For the trilogy course, you need to know what an alkene is, and that's a substance containing a double bond. So there must be at least 2 carbons, of course, because the double bond must be between 2 carbons, because carbons can make 4 bonds, hydrogen can only make 1 bond. So that's an alkene. For trilogy, you don't need to know the name of it, but that's ethene. Eth because it's 2 carbons, ene because it's an alkene. And propene, which we will really struggle to draw. It's got 3 carbons. Propene, 3 carbons. And it's got it's an alkene because it's got a double bond between the 2 carbons. Notice that every carbon makes 4 bonds, and so be careful when you're drawing these. Carbon's got 2 bonds to another carbon, so it must need 2 more bonds, one with hydrogen, one with hydrogen. This middle one is making 1, 2, 3 with carbons, so need 1 more hydrogen, and we've got 1, 2, 3 hydrogens attached to that terminal carbon, and that's propene. And there are others as well, as butene and pentene and variations on those, which we don't need to worry about right now. In this video, I'm only going to talk a little bit about what the trilogy students need to know about alkenes, and there's much more detail to come. So, alkanes are what we call saturated and have 2 hydrogens for every carbon plus 2. So this is CH4. So 1 times 2. If N is 1, because 1 carbon times 2 is 2. Add 2, you get 4. C2H6, C3H8, C4H10. All of those numbers, all of those ratios between carbon and hydrogen match the general formula there. CN2N, H2N plus 2. And the alkenes are all CnH2n. You need to know that alkenes are typically used to make things like plastics. You need to know that alkenes are more reactive than alkanes, and they will therefore undergo a reaction which alkanes won't undergo. Specifically, they will react. Alkenes react, this is the last thing I'll do on this video, alkenes react with bromine water. When you're doing that, if you ever do that in the lab, you have to give it a really good shake. So alkenes react with bromine water. You probably put the alkane in a test tube, chuck in a little bit of bromine water, not too much, and then give it a really good shake. And the bromine water, which is Br2 dissolved in water, this stuff is orange. And when you shake it with alkenes, it reacts very, very quickly with the alkenes, and the bromine no longer exists. you've generated something else, which I'll do in the triple video, and the product is colourless. So it goes from orange to colourless. The bromine water goes from orange to colourless. And so this is a way of checking that your cracking has worked. Remember that cracking, you make an alkene and an alkane, and you can prove that it's worked. It would be a mixture of alkene and alkane. You could chuck in a little bit of bromine water, give it a shake, and the alkene would turn the bromine water from orange to colourless. There's a nice picture of it actually in the down there, which you might have done. I like the fact they've got a lid because it's quite a stinky process. There we are. That'll do. Hope that was useful. See you in the next video.